is inside S, i.e. S of n naught is true for some n naught inside the positive integers. Step Step 2 is write the induction hypothesis. Which is n is an integer such that n is greater than or equal to n naught, and n is inside set S, i.e. S of n is true for some integer n such that n is greater than or equal to n naught, or you can say do same thing for some k. And then step 3 is show that n plus 1 is inside S, or you can say similar thing as S of n plus 1 is true. Then we have this example. And this example says that we need to prove 2n plus 1 is less than or equal to 2 power n for all n greater than or equal to 3. So we have the statement S of n is 2n plus 1 is greater than or equal to 2n plus 1 is less than or equal to 2 power n for n greater than or equal to 3. We need to show that S of n is true for all n is greater than or equal to 3. Step number 1 is consider n is 3, then show S of 3 is true. So which you can just put 3 and you can say that 7 is less than 8, which is true. Now we suppose for step 2 that 2n plus 1 is less than or equal to 2 power n, and S of n is true for some n is greater than or equal to 3. Then we consider S of n plus 1, which is going to be this. And then we will just consider the left-hand side of this statement. This is the left-hand side. If you just open it, it will be this one, 2n plus 2 plus 1. And if you write it, rearrange it, you will get 2n plus 1, which we already know that which is true as 2 power n. So that is 2n plus 1 is less than or equal to 2 power n. So we can replace this part with this part. So 2n plus 2, where S of n is true. And then we can get 2n plus 2 power n again, because n is greater than or equal to 3. And where this 2 is less than or equal to 2 power n. So we can also again get 2 power n. And then we can write that this is equals to 2 power n plus 1. Hence, this statement n plus 1 is also true. And then by the principle of mathematical induction, this statement is true. That S of n is true. Okay, perfect. We can also write some other example, but let's talk about the division algorithm. Now we have a theorem number 1.2.3. The name is division algorithm. Let x comma y be two integers with the condition that y is not 0. Then there exist unique integers q and r such that we can write x as q y plus r, where our r is between 0 is less than or equal to r is less than absolute value of y. We can prove this by using the principle of well ordering and some other arguments. But that would be a long argument, so there is no need to prove it. I will just say that this q is the quotient of x and y when we divide x by y is quotient of x and y on dividing x by y, and then r is the remainder of x and y. There's a corollary for this. It says that for any two integers x and y with the condition that y is greater than 0. In the theorem, we have a condition that y is not 0. Now we have a condition that y is greater than 0. Then we can say there exist q and r such integers such that x can be written as qy plus r. Now r have a different bound. Now we don't have to consider the absolute value. And we can prove this simply by saying that by Theorem 1.2.3, there exist unique Q comma R such that we can write X as QY plus R, where R was between 0 and absolute value of Y. Now, since Y is greater than 0 now, and absolute value will always be equals to, in this case, is Y. So hence, X is QY plus R, where R is between 0 and Y only. Okay. Perfect. Then there are some other properties about X, Y, Z, the integers. We can say, so let X, Y, Z be integers with the condition that X is not 0. Suppose X is a divisor of Y, so divisor of Y, and X is a divisor of Z, then for all integers S and T, X divides Sy plus Tz. When we write, so when we write this, it means X is said to divide Y, or similarly we can write X is a divisor of Y. This is the notation. And if it does not divide, then we will just slash it. X does not divide Y. These are the notations. There are common divisors. So there is a definition, which is that we have two integers, a non-zero integer C is called a common divisor of X and Y if C divides X and C divides Y. There's another definition for greatest common divisor. It says that a non-zero integer D is called a GCD, greatest common divisor, of the integers x and y if one, if D divides x and D divides y, 2. For all C inside Z, if C divides x and C divides y, then C also divides D. Then D will be the greatest common divisor. Now we have a theorem. (1.28). It says that we have two integers with the conditions with either of them is 0, either of them is not 0, x is not 0, or y is not 0, then x and y have a positive GCD D. Moreover, there exist elements s comma t inside the set of integers such that D is sx plus ty. And to prove this, you can give the proof of this. What we can do, so let's introduce a set, which is mx plus ny, given that m comma n are the integers, where mx plus ny is greater than 0. We suppose x is non-zero, not 0. Then absolute value of x will be equals to following values. It can be x if x is 0, greater than 0. It can be minus x if x is less than 0. It can be 1x plus 0y if x is greater than 0. And it can be minus 1x plus 0y if x is less than 0. Hence, order of x is inside S. Absolute value of x is inside S, and so S is not empty. By the well ordering principle, S contains the smallest positive integer cd. So by principle of well ordering, S contains a smallest positive, smallest element inside the positive integers. D. We now show that D is the greatest common divisor of X and Y. So then we now show that GCD of X and Y is D. And since D is inside the set S, there exist these two integers inside these two integers such that D can be written as Sx plus Ty. First we show that D divides X and D divides Y. Since D is not zero, by the division algorithm, there exist integers Q and R such that X is DQ plus R, where 0 is less than R is less than absolute value of T, which is D. Thus, R is X minus DQ, which is X minus Sx plus Ty into Q, because D was D has the value of D has the value of Sx plus Ty. So we just replace that. And if we replace that, we will get we will get 1 minus Qs into X plus minus Q into Y. And we know that we suppose that R is greater than 0, then R is inside the set S, which is a contradiction, since T is the smallest element of S. R is inside S, which is a contradiction, because D is the smallest element in S and R is less than D. Thus, R is 0. This implies that X is DQ, and so D divides X. Similarly, D divides Y, hence D satisfies one of definition of GCD. Suppose C divides X and C divides Y for some integer C, then we know that C also divides Sx plus Ty because we have mentioned this before. So i.e. C divides D. Thus, D satisfies condition 2 of definition of GCD. Hence, D is a GCD of X comma Y, and we have the proof. Okay. Then we can give so many examples about this. That let's say, let's talk about some example. So we have X is 45, Y is 126, then GCD of X comma Y is 9, and 9 can be written as 3 into 45 plus minus 1 into 126. And we can write this more as 129.45 plus minus 46 into 126. So we can talk about these S and T if we have X and Y. So you can guess that Here S is 3 and T is -1. Here S is 129 and T is -46. Or there is another way to solve this problem as number 1. Number 2 is, you can say that 126 is 2.45. 2 multiply 45 plus 36. Further, we can write 45 as 1 into 36 plus 9. And we can write 36 as 4 into 9 plus 0. Thus, 9 is GCD of x comma y, which is GCD of 45 126. Also, 9 can be written as 45 minus 1.36. We can also write 45 minus 1 into 126 minus 2 into 45. We can also write 3 into 45 plus minus 1 into 126. That means S is 3 and T is -1. Perfect. Now we can talk about some primes. So we have a definition. Number 1, which says that an integer p greater than 1 is called prime. The following, if the only divisors of p are, if the only divisors of p are plus minus 1 and plus minus p. Number 2, two integers x and y are called relative prime or